When you watch a quadcopter execute a flawless hover, it looks like it's defying gravity, but staying still requires thousands of microscopic adjustments every second. To manage this balancing act, the drone relies on a high-speed sensor called an IMU. Think of it as the drone's inner ear. It feels the slightest tilt or vibration and tells the motors exactly how to react to keep the aircraft level. This diagram shows a hidden flaw in that inner ear. Because the sensor is so sensitive to vibration, it builds up tiny errors over a long flight. Its internal balance slowly tilts away from the true horizon, a condition called drift. As the diagram zooms out, you can see the physical danger. The drone slides sideways toward a wall, but its digital brain falsely believes it is perfectly level. Lightning-fast reflexes are useless if the machine loses its sense of reality. To stay airborne safely, it needs a way to look outside and check its own math. To fix that dizzy inner ear, we have to look up, way up, into Earth orbit. This shows our first backup system, GPS. This network of orbiting satellites functions like a glowing global video game map. These satellites beam invisible coordinates down to the aircraft, providing an absolute, unmoving reference point for its location. Unlike the inner ear, these space anchors never get dizzy. The drone uses this slow, perfect map to instantly correct its tilted balance and stop that dangerous drift dead in its tracks. But there's a catch. Satellite data is very accurate, but it's slow. It only updates a few times a second, meaning it cannot react to sudden wind gusts. To survive, the fast inner ear and the slow space map must work as a team. But what happens when the drone flies into a deep, rocky canyon or under a thick concrete bridge, where those satellite signals are completely blocked out? Without GPS, the drone is blind to the sky. To keep from drifting, it has to rely on a different survival tool, ground vision. If you look right underneath the aircraft's belly, you'll find a tiny camera lens actively scanning the ground below. This is optical flow. The drone's computer is digitally locking on to the textures of the rocks and grass beneath it. It works like a passenger looking out a car window, watching the road rush by to judge speed. As wind pushes the drone, the camera tracks how many pixels those rocks move to determine its direction. This raw speed data is sent instantly to the drone's brain, serving as a perfect replacement for the missing satellite coordinates. This belly camera is the reason drones can hold perfectly still indoors, deep in forests, or anywhere the space anchors are broken. It gives the drone absolute independence, turning the ground itself into a reliable map when the sky disappears. To see how all of this comes together, we have to look at the central processor. This board manages every signal the drone receives. The brain runs a clever digital process called sensor fusion. It acts like a master detective, constantly weighing the evidence from its 3 super senses to find the truth. This diagram shows the fusion in real time. The brain cross-references the fast inner ear against the slow space map and the local ground camera, merging them into one single, stable sense of reality. This makes the drone incredibly resilient. If a leaf covers the camera or a bridge blocks the GPS, the detective instantly trusts the remaining senses to stay airborne. These invisible senses are what allowed the Ingenuity helicopter to navigate the thin atmosphere on the surface of Mars, proving that these simple rules of physics can help us explore new worlds.